We're happy today to have Richard Ng from LSU and MSRI, who is going to be telling us about signatures of braided fusion categories and Witt groups.
Okay, thank you. This is my first time to speak online, so whatever experience I have now will be, I can learn it for the future. So I would like to talk about this because I think last time I have a preview of what I'm going to talk about, but actually I left out a big chunk, which is a signature, which is actually very essential to the whole paper. So this is a joint work with Eric, my postdoc, Yilong Wang, and Qing Zhang, which is another postdoc member in MSRI. So whatever I said here is already posted in the archive. So if I make any mistake here, you can correct me, or you can have any comment, let me know. All right, let me see. Okay. Oh, looks like okay. Let me start with the motivation here. Basically, it's two questions. The whole paper is question motivated. So I begin with Ising modular tensor category, and which is a rank-free pseudo-unitary category with order T with 16. So I put it such a way so that like it won't have 16 unimodular modular tensor category Ising. I just talked about 8 of them. So the Witt group of the non-degenerate braided fusion categories is actually W is the Witt group of the non-degenerate braided fusion category. W pointed is the subgroup generated by the Witt class of pointed ones. Then the open question, one of the open questions is like the Ising class in the Witt group has a square root, but how many of them? So does the equation x squared equal to I have any infinite many solution in the Witt group quotient by the pointed? If you include the pointed, you could have infinite many because you have a lot of order 2 in the pointed subgroup. So another question is like actually it's a conjecture. It's offered by Davydov-Nikshych-Ostrik. Basically is the super-Witt group 2 sub 2. What is this subgroup? It's a subgroup generated by the finite order classes of completely isotropic as simple braided fusion category. So we know this subgroup has exponent 2 actually. It's proved in their paper. What was not known was that this group has infinite order. This is also open. So what we like to address is like that the answer to both questions are yes. And the first one actually implied the second one. So this is the motivation of the talk and also the paper post in the archive. All right, so any questions? Okay. Let me see. So please interrupt if you have any questions. So I begin with the notion of signature of a totally real number. So an algebraic number R is called totally real if all the Galois conjugates of alpha is a real number for all automorphism of Q bar, which is the algebraic closed field of in C over Q. So so for each of them, then you can define for a totally real number, you can define something called signature, which is actually a function. So if let's suppose alpha is not 0 and it's totally real, the signature actually is a function from the Galois, absolute Galois group 2 plus or minus 1. Basically, it's a sign. But you can rewrite it as like sigma alpha, which is a real number, divided by the length. So end up you get a sign, either 1 or -1 for any sigma belong to the Galois group of Q bar. So this element always have order, well, it's always as order 2. But then you can use it to define totally positive real number, which is a non-zero, totally real non-zero number when it's called totally positive when the signature actually constant function 1. So somehow the totally positive number are kind of like a kernel of this signature function. If you would like to extend this signature to non-zero element of totally real field, then you actually get a kind of a group homomorphism by computing the signature. So basically, we're using this signature to define the invariant for any fusion category. So let me just give you some example, which is trivial enough so that we don't need to explain a lot. 5 is totally positive. No matter what Galois conjugate of 5 is still 5, so it's always totally positive. But square root 5 is not totally positive because you could get negative square root 5 when you do the Galois conjugate. So you have sign and you have sign there. You have negative 5, square root negative 5, and positive negative 5. Depends on the automorphism. So basically, there are 2 types in this case. So another example, which is crucial to what we are going to talk about, which is the global dimension and the Frobenius-Perron dimension. Both of them are shown to be totally positive cyclotomic integers. So when you have a totally positive cyclotomic integers or totally positive integers, you can actually take the square root, just like you take the square root of 5. Then you get a totally real number. So both of them are. And their signature actually are different in general. So, and we do not know, but we do not know whether these numbers are actually cyclotomic in general. So if you have a, well, in general, we don't know the square root of dimension C is, but if there's a braiding, if C has a braiding, we can show that the square root of dimension C is a cyclotomic integer, but in general, we actually don't know. So now we can use it to define the notion of signature of a fusion category and rebuild from there. So let C be a fusion category, and the signature epsilon C of C is simply a signature of the square root of the Frobenius-Perron dimension of C. So this one you can just, it's well defined. So remember, it's a function of the absolute Galois group. So then you can do it for the categorical dimension too. So both of them I still call signature. One is signature, I call epsilon C, the other one is called epsilon prime C. So the prime represent the categorical dimension signature. Sometimes they're the same, sometimes they're not. So when C is pseudo-unitary, then they will be the same because the global dimension is the same as for Frobenius-Perron in this case. But in general, they're different. So, and they can be very different. For example, you take this modular tensor category was SO5 of level 3/2, and then you get some interesting, the distinction is pretty high. So now look there, this is the set of function from the absolute Galois group to plus or minus 1. Plus or minus 1 is a group, it's a multiple group. So therefore, this one can be treated as an abelian group by using the pointwise multiplication. And it's not difficult to see that if you have 2 fusion category, then you can take the Deligne product and compute their corresponding signatures, epsilon and epsilon prime. Then they respect the Deligne product of the 2 fusion category. So on the other hand, if C is the center or the drain field double of a fusion category, then the dimension is going to be, let's say the global dimension is the square of the global dimension D. Then when you take the positive square root, so by the way, when I talk about fusion category, I talk about fusion category over the complex. So I don't want to split here. So that means all these numbers are a complex number, and then they are totally real numbers. And then you take the square root, I always take the positive square root. So then therefore, when dimension C is dimension of D squared, then you take the square root just dimension of D, because we know dimension any fusion category is totally positive. Then therefore, if they can detect, at least partially detect, whether a fusion category is a trivial double or not by using the signature. So the signature of a trivial center is always 1. It's trivial signature there. So both of them. Okay, so in a sense, we kind of kill all the double. The signature kill all the double. So now we record the definition of Witt group for the braided fusion category with ring C. So we say it's non-degenerate if this the simple object of the centralizer of C, that's only the trivial object. So if X is irreducible, which is centralized, all the other simple object, this can only be the unit object. In this case, we call the braiding non-degenerate and underlying braided fusion category non-degenerate. So 2 non-degenerate braided fusion categories C and D are correct equivalent if there exists fusion category A and B such that the Deligne product of C with this center of A is braided tensor equivalent to the Deligne product of D, Deligne product with center of B. So when you compute the signature on both sides, then you can see that they're equal. So because of the center contribute nothing to the signature. So therefore, you can see that the signature will preserve the, stabilize in the Witt equivalent classes. So then we can define the signature of a Witt class of C as the signature of C. So it will be well defined for the Witt class. So we know that the Witt class form a group under the Deligne product. So, and then this one, epsilon and epsilon prime, will extend to a group homomorphism. So this well defined. So this story of the Witt group for non-degenerate braided fusion category is I think it's easy to follow. But when we go to the braided fusion category over some symmetric category, they're more technicality, but the idea is still very similar. So now we know that the signature of it can be viewed as a group homomorphism on the Witt group to the functions of the Galois group 2 plus or minus 1. So any questions? So any of this Witt class give you a function from the Galois group 2 plus or minus 1. And this is respecting to the Deligne product. So now we extend to something called the Witt group of non-degenerate braided fusion epsilon category. So, which is somewhat like the non-degenerate braided fusion category, except that it may not be trivial. The mutual center could be some non-trivial symmetric fusion category. So let me just go over it quickly instead of at least you see the whole outline is very similar to the Witt group. So let's see the braided fusion category braiding C, and the mutual center is simply the full subcategory with the object in C which centralize all other objects in C. So in the non-degenerate case, this is only consists of the sum of unit objects. But in general, this is not the case. But nevertheless, the mutual center is a symmetric fusion category. So then you can use the Deligne's result. This is some representation of finite group. So therefore, this one is always pseudo-unitary and integral. So now I just basically quickly go through the paper of the Davydov-Nikshych and Ostrik on this. So let's see a symmetric fusion category. A non-degenerate braided fusion epsilon category is a braided fusion category C together with a braided tensor equivalent. I require to be equivalence T from this epsilon to C prime. So basically, it's a pair. It's it's a braided fusion category together with this embedding T. So you can talk about like the limit product over epsilon, which is like suppose C and D and a non-degenerate braided fusion epsilon category, we can define the tensor product over epsilon. So this is again a non-degenerate braided fusion category, epsilon category. And you can also define the Witt equivalence of these non-degenerate braided fusion epsilon category. Basically, if C and D are Witt equivalent, if there exists a fusion epsilon category A and B, now the fusion category, fusion epsilon category A and B, I didn't define here, but it's somewhat like the case of a braided fusion category, but you have to define by using the central functor. Anyhow, I skipped this technical detail. So then you take the limit product of C with so-called the center of A epsilon, which is actually the center of A, which is the centralized of epsilon in center of A. So the C A epsilon is simply another braided fusion epsilon category. So you tensor them together and it's equivalent to the other tensor product as a braided fusion epsilon category. That means you have to care about the underlying embedding of, compatible with the underlying embedding of epsilon to these categories.
Richard.
Yes?
Do you really not care if epsilon is Tanakian or non-Tanakian?
No, doesn't matter at the moment. Okay.
Yeah.
So then you define the Witt equivalence of them. Then you can see that now I can define the signature of homomorphism. So it's somewhat like the Witt group, except that the epsilon you have to take care of this factor epsilon or input data epsilon. So the Witt equivalent class of non-degenerate braided fusion epsilon category form a group under this limit product over epsilon, just like the ordinary one. And in particular, the Witt group that I mentioned at the beginning, which is actually this notion is W-vec. So I don't want to use W-vec, it's too much to write. The other one is the super vector space, which is not Tanakian. So I just simply write SW and I call it super-Witt group. So it's basically these are the two Witt group that I'm going to talk about. So now I can define the signature for this braided fusion epsilon category. Now, instead of using epsilon again, because I need to adjust it, so I define two versions of it. One is given by the Froebelian spherical dimension, the other one is given by the global dimension. So namely, you have to adjust the factor of epsilon. So basically, if you for the I epsilon C, I need to define it as the signature of C times the signature of epsilon. So the other one is a prime correspond to the global dimension, which is the signature, the global dimension signature of C times the signature of epsilon. But in this case, I don't need to distinguish both signature for epsilon because they're the same. It's a pseudo-unitary one. So this adjustment, you can see that sometimes it's there, sometimes it's not there. Depends on whether the group or the underlying category is a square or square-free integer. So if it's square, then you don't do anything. If it's square-free, then you have a sign there. It will play out when you compute it. So what we can show is that these signatures are well-defined group homomorphism on W epsilon to the other group. I mean, to the group is like a function of the epsilon Galois group 2 plus or minus 1. So basically, we use, this is simple to define, but actually it's not easy to compute. But you have a lot of invariance because of that, because each Galois group automorphism gives you an invariant of the Witt class. So that is the key point of doing that. So Now, now we go back to, let me see, I hope I didn't skip. Okay, we go back to the super-Witt group setting. So again, it's a result of DNO, which is again it's like Davydov-Nikshych-Ostrik. There's a map from a group homomorphism, the Witt group to the super-Witt group. Basically, just give a class of modular non-degenerate braided diffusion category in W, then I just tensor with the supervector space, and the corresponding class will be the image of S. It's a good defined group homomorphism, and the kernel is given by the I forget the right angle bracket there. It's actually generated by Ising, so that means it's a group of order 16. It's a group of order 16. So you notice, and this signature actually is compatible with these homomorphism. So if you compute the signature from W directly, and you can compute it on also the super-Witt group under, and then you have this commute diagram via this mapping S. The same for the other one. So somehow they are very compatible with the structure of this Witt group and super-Witt group, or W omega if you want, W epsilon if you want. So basically, they finished the first part of what I want to say about the signature of these Witt groups, all these Witt groups. So, any questions? Okay, and then move ahead. Now, defining is one thing, and then computing it is another thing. So, the first thing I would like to show, how does it relate to the other invariant? Actually, this is I just reverse what we found and present it here. In fact, we didn't start with the signature, but we found the signature is a key component for a whole thing. So we go back to the higher central charge. So we call that the higher central charge require a Rubin structure to compute. You cannot compute the higher central charge without spherical structure. So there's some discrepancy here. So for the previous one, you just need a non-degenerate braided diffusion category, but for the higher central charge, you need a spherical structure or Rubin structure to compute. So it depends on your choice of spherical structure. You choose different choice, it will give you different thing. So the Witt group just deal with the braiding, so you cannot choose an arbitrary spherical structure. So end up, if you want to deal with the problem or using the higher central charge, we need to deal with some braided diffusion category with a canonical Rubin structure, which is the pseudo-unitary one. So I begin with a modular category with a Rubin structure theta. So now, as I said before, these Gauss sum and central charge are all defined by using the Rubin structure or the spherical structure. So if you don't have a canonical one, you're not comparing the underlying braided structure. So this is what we found with a previous paper with Sopere and Wang. So basically, we define by using integer. This is it's the inconvenient part using integer. So for any integer n, such that n is readily prime to the order of the T matrix, then we can define two things. One is the higher Gauss sum, which is the sum of dx squared times theta x raised to the power n. And we can show that for such n, this is always non-zero. And then once you know it's non-zero, you can write down so-called the higher central charge, which is I call it C sub n, C, which is actually you can say it's the angle of this Gauss sum. So you take the Gauss sum, divide out by the length. So it's the argument of the complex number. So, and we show that there's always a unity. This is what I just said, just an angle. And this is we call it a higher central charge. So when when you have two Witt equivalent pseudo-unitary modular tensor category, when I put the word pseudo-unitary there, I assume that the underlying spherical structure is the canonical one, which will give you the Frobenius-Perron dimension. So I put that word there just to let you know that I'm using the underlying canonical spherical structure or ribbon structure. So if they're a Witt equivalent, then this higher central charge will be equal under the condition that this n is relatively prime to both of the order C and D. So you can see that the order of T, C and order T, D could be quite arbitrary because I can let any center put in there with an arbitrary number there. So there's some ambiguity here, but if I can choose an n so that they equal, so that they're relatively both for T matrix, then I'm fine. But so it poses a problem that we have some difficulty to compute it, but it's also computable. You can actually implement to computer to compute the higher central charge of finitely many pseudo-unitary modular categories. So now this poses some difficulty here because the setting requires some number relatively prime to the order of the T matrix. So we would like to reformulate it by using the absolute Galois group. So we can do it in the following way. So let n be the order of the T matrix. And for any automorphism of the Galois group, it's the absolute Galois group, so I can restrict to any finite Galois extension over Q. I can restrict to the cyclotomic field generated by the n fluid unity. So then there will be a unique n, modulo n, such that first of all n is relatively prime to 1, relatively prime to n, and it will send the n fluid unity to such power, to little n power. So there's only one such n modulo the big N. So for each sigma, I have only one such n. So I have no ambiguity to write down the underlying central charge because of that. And I can define my central charge of sigma of C as this central charge. So this is the key point here. So we formulate the central charge in terms of the element of the absolute Galois group instead of integers. So once you do that, then you can write down a formula. So this is the theorem of four of us. So let's see be a modular category, this arbitrary modular category now. So, and sigma is an element in the absolute Galois group. So then you can compute this C sub C sigma. So you can write down such a formula. So what is the first component, which is epsilon prime C sub C applied to sigma inverse, which is the signature, the global dimension signature of C. And second one is the Galois conjugate of the first central charge of C. Now the third one is a bit ambiguous if you don't you're not used to it, which is that gamma is any third root of the first central charge of C. Any third root. But when you take the quotient, this is a well-defined number. No matter which gamma you choose, you get the same number. So what is that? This is actually the twist of the object of the Galois permutation of sigma of 1. So actually, it's a special meaning for this quotient. So, but you can see that the third factor just depends on sigma, and also the first central charge. So then you can see that if both C and D are Witt equivalent pseudo-unitary modular categories, then the first central charge will be the same. It's proved in another paper with Muger and DNO or DMNO. So, and because they are Witt equivalent, their global dimension signature as the same. So one can take the same third root for both category, gamma, because they have the same first central charge. So you can see now, then because of this setting, these two, the value of C sub C and then the C sub D of sigma are the same. So in other words, this this function is independent of choice of the Witt class of C, the representative Witt class of C. So now we can generalize to as a function. Now we define the C to the Witt group generated by pseudo-unitary modular categories as applied to, if applied to this class is equal to the C sub C. So it will be well defined, and moreover, it is a group homomorphism. So this is the key of the whole thing. I mean, so we would like to have such a group homomorphism so that we can determine the group structure generated by finding many elements, or even infinitely many elements, by using this group homomorphism restrict to this subgroup. So it's how we get the group structure of some subgroup generated by some finding element or countability of any elements. So first of all, this is a well-defined group homomorphism, and we also know the kernel of this. So what is this? They are the pseudo-unitary. They are given by the pseudo-unitary modular category with trivial signatures and first central charge 1, basically. So the other part is basically play no role. So although I may not be able to compute the higher central charge, but this will be sufficient for me to get all the higher central charge of C. When I say all, I just mean those relatively prime to the order of the T matrix. I don't know the other, which is even non-zero. Okay. Oh, I have a typo here. So as usual, I just write down W point to be the subgroup of WUN, again, generated by the class of pointed modular category. So the pointed modular category are always pseudo-unitary. So no problem with that. The typo, it just says W sub UN. And I define the W point sub point P, which is a subgroup of W point generated by the pointed modular category. Oh, another typo given by a P group. So so basically, it's just the classical Witt group given by the P group. So, but then in this W point P, there's a unique class I call AP here, in which for each prime P, so that which is like a signature trivial, but the first central charge is -1. In other words, it is order 2, but it's not due to the signature. It's due to the charge completely. So each of these pointed P group or pointed modular category of order P power has one such class, exactly one. So, but then that's what I try to allude to. If I try to understand the structure of some subgroup generated by some modular category in the Witt group, I just try to restrict to this subgroup and see what I get as an image or the kernel. Then I can understand the structure. Of course, I want to know the kernel of the whole thing, but actually I find it for some cases. So when this, I call this C maybe the higher central charge group homomorphism, or simply central charge group homomorphism. When you restrict on W point P, is injective. So that means you can tell the group structure by using the image of this Witt group. So, but on the other hand, if you restrict the central charge group homomorphism to all the pointed or W pointed, basically the subgroup generated by all the pointed modular category, then you have a kernel, but kernel is always in pair. It's generated by element in pairs. Let's put it there. So they are given by A. Oh, the prime, I have another typo. The prime is actually above P. So it's given by the class of AP times AP prime. So it's always generated by a pair. So if P and P prime are different, you have a non-trivial class. But if P and P prime are the same, actually you get a 1. So so you want to pick, actually you want to pick P and P prime a distinct prime number. So this is the group generated by these product of pairs. So now, so in general, they are not injective, even for the torsion part. But then, and nevertheless, sometimes they are injective. Then we can use it for understand the group structure, at least part of the Witt group. Now we go back to the motivation at the beginning, which is the square root of the Ising modular category. So we fix a Ising modular tensor category. Well, for example, we take the SL2 level 2. Then we consider this quantum group category. So for simplicity, I just write C sub R, which is the quantum group SO2 R plus 1 at the level 2 R plus 1. So this level is not the order of the root. So just level. And somehow there's a mistake here. Anyway, so in the DNO, they show that this the square of this is always some power of the Ising. So any of them is some power of Ising, where L is odd. So you can see that therefore each of them has order 32. And when because we know the kernel of this S homomorphism from W to the super-Witt, and all these elements has order 2 under the image of S, which is the image of S of these elements has order 2. So on the other hand, that means like the group generated by CL, the image of under the image of S is elementary 2 groups. So we can talk about the image of the pointed part. It's called SW pointed, and SW2 is a subgroup of SW generated by the finite order Witt class of completely isotropic S simple braided fusion categories, a mouthful. But the other one, SW infinity, which is the one with infinite order. So in their paper, they already showed that this SW2 is an elementary 2 group, but could be infinite rank, could be finite rank, which is not known. And they show that there's a decomposition of the super-Witt group, which is the super pointed part, direct sum with the SW2, and direct sum with SW infinity. So this will make up the whole group SW. So here is come back to their conjecture again, so more precise term. So they conjecture that the image of this CR, which is the quantum group SO of 2R plus 1 at the level 2R plus 1, are actually in SW2. This one is, I still don't know whether it's true or not. So in general, or even a big part. So the second one is that they are linear dependent over Z2, of course, because they are elementary 2 group. They form an elementary 2 group. So therefore, either it is finite or they could be dependent. I don't know. But then this is what they conjecture. And then the last one, because of these, particularly the first 2, that will imply SW2 has infinite order. So the first one largely come from the first 2. If you can prove the first 2, then you can prove the first one. But instead of proving the first 2, we can establish the third one. We can partly establish the second one. So the idea is using this central charge homomorphism. We restrict to the subgroup generated by this CR in the Witt group. So we are not able to determine everything, but we are able to decide for some infinite subsequence of this CR. So namely, we can find an infinite subsequence of CR so that the image under S are linearly dependent. So in this case, I say SW2, I don't mean they're in SW, but then you can project onto the SW2. So again, they're still linearly dependent. So this implies that SW2 has infinite order, if you can show that. So, and then this one, this result actually follows from the fact that the pre-image has infinite order as a group in this quotient. So this group are generated by actually the roots, the square root of the Ising, so to speak. Now, to proceed, actually, we need to compute the signature of these non-degenerate braided fusion category. So, but we can use the data of these quantum group modular category. At least we can compute a formula for the square root of their global dimension, or for Business dimension. So, and this actually is essential to determine the signature of these categories. So we can write the square root of dimension is a product of signs and square roots. So each of them can be compute, if it's not efficiently, at least it's computable for the sign of the Galois group action. So the signature of the Galois action. So you can do it by each term or the product so that you couple it up together. So we still could not show for each R, unfortunately, but we can show it for a certain sequence using the formula. So what is this infinite sequence here? So I'm going to be more technical now because I need to generate an infinite sequence of this integer sequence, which allow me to compute the signature, at least partially of their signature. So what is this infinite sequence? I probably will think a little bit horrible, but we are not smart enough to get the general setting. So here we go. So let Z be a non-negative integer. I set L to be 4Z plus 2. Somehow is kind of manufactured. And I decide AZ0 to be 2L plus 1. So first certainly is an odd number. And then now I define the infinite sequence A sub C recursively by setting the following. So I require the following one, A, Z, n plus 1 to be congruent to 2L plus 1 modulo 8L plus 2. You may find, so why do you do that? Well, just because we're not able to compute up the signature arbitrary CR, we can only compute certain. This is become the choice. It's the technical choice of the sequence. And then the other one is, the other condition I require is AC n plus 1 is relatively prime to all the preceding terms of A sub C. So the why I can always get such a thing, well, just because of the theorem of Dirichlet. So we know that it's easy to see that the GCD of 8L plus 2 and 2L plus 1 is 1. They're relatively prime. So then you apply the Dirichlet polynomial theorem, you can get an infinite sequence. They are prime actually, satisfy this condition. So in particular, I can find those weaker versions. So I can always proceed to find the next one, AZN plus 1. This is all because the Dirichlet polynomial theorem. This one will repeat again. So let you give you a look of the, say, when Z go to 0. And the first one, in this case, the L will be 5. And then like you continue in such a format, and then you find the next one, which congruent to 2L plus 1 and relatively prime 5, and to 23, and so on. and you generate sequence. You can see some of them are not prime. For example, 77 is not a prime. So you can recursively define a sequence. You can write it down explicitly, but of course, I don't have a formula for it. So once you have such a sequence, we use a sequence. So this sequence we need the format of this sequence. So any subsequence of this sequence will work fine, but I need some sequence like that at the beginning. So I take any subsequence of this specific sequence, AZ. This AZ is parameterized by arbitrary Z, which is non-zero integer. Z is a non-negative integer. So we denote it by the group GFN, which is the subgroup generated by subgroup of this weak group, generated by the classes CF0, CF1, and so on up to CFN. So basically, I take the first n term of this sequence F and look at the corresponding CR, the corresponding quantum group category, and form the subgroup generated by these classes. I call it GFN. So you can take the direct limit and then you get the GF. So you basically union all of them. Does it make sense to everyone? So, because GF is a direct union of the G sub Fn, then you can just basically, if you understand each of them well, then you can understand FGF. So here's a theorem that we prove. So let n be any infinite subsequence of A sub C. Then first we show that the restriction of each of these finite component GFN is injective. So in other words, we know the structure of this group if we know the image of this the classes, and we generate a group by the image of these classes. Then we know the group structure of this group. So in fact, we can show that this is isomorphic to the cyclic group of 32 and direct product with the elementary 2 group of rank n. So each n gives you such a group structure, of course. And then you model out by this basically image under the map S. So if you take the quotient, it's always isomorphic to Z mod 2 raised to the power n plus 1. So it's always elementary 2 group, the same as the number of generator. So that means they are linear dependent. That's indirectly show. And the other one is, that means if you restrict the whole GF, of course, it's injective on each component, then it's injected on the whole GF using the direct union. And GF in this case is isomorphic to this infinite group. So it's Z32 plus the infinite rank elementary 2 group. So, and you look at the image of this group, is always Z2 to the n, where n is the set of all natural numbers. So it's the infinite ranks elementary 2 group of elementary 2 group. So this is the beginning point of this, at least address one of the problem that we start with. So in this case, we can see that the weak class of the Ising model tensor category I has infinite many square root in W. Basically, I just pick any F like that. Then the square will be I, and then I get an infinite ranks. And in particular, and also, if you look at the image of this sequence, just pick the whole sequence, A sub C, because F is arbitrary, I can pick the whole sequence, and look at the image under S, then this will be linear dependent in SW. So as I said, we still don't know whether this sequence lies in SW2. We do not know. So it could be the case like if some component is in SW2 with some pointed part of order 2. So we don't know how many are there, and it could be, but we actually no idea. But anyway, each of these elements in SAZ, which is the image of the sequence given by the A sub C, I can project to SW2. So, but then the projection, we can show that is infinite. So therefore, we can show that the SW2 has is infinite rank. So to proceed, we use a prime sequence of A sub C. As I mentioned before, A sub C is always contain the prime sequence, a prime sequence by using the Dirichlet prime number theorem. So we particularly pick the prime number sequence, but I don't know what they are. Probably I can generate it, but you can only know it exists, but hardly write down the formula for it. So I pick a prime sequence of AZ, and we can use it to generate the group in W, which I call GP as before. This one has only, when it intersects with the pointed part, can only be the square of the Ising, generated by the square of the Ising. So the computation actually also by using the central charge homomorphism. So this proposition allows us to prove this formula. So when you apply, basically this part is the image of a GP modeled by the superpointed part. And this is isomorphic to GP mod I. So, which is also isomorphic to this infinite elementary 2 group. So, but look at the first term actually is a subgroup. You can consider as a subgroup as SW2 because all of them has finite rank, finite order. So therefore it cannot be in the SW infinity. So therefore, in particular, SW2 has infinite rank. So this is actually complete the story that I start at the beginning, and we can only partially answer the question by using the signature or the high central charge, but that's why I want to say. So I hope so I didn't lose everyone.